Giulio Scelfo. Here visiting us virtually, giving us a talk about gravitational waves and H1 intensity mapping cross correlations. Giulio did his master's at the University of Padua, but he did his final project in Barcelona. That's how I met him. And then he continued doing a PhD at SISSA, and is now in this finishing up. So yeah, excited to hear what you're going to say.
Okay, so thank you very much, Ben, for the introduction, and thank you all for having me here giving this talk. So today, my talk will be based on this work we published on JCAP early this year with Marta, Alvise, Lumen, Andrea, and Matteo. So what I'm going to tell you about, it's a series of interesting things you can do by studying the cross correlation of two completely different tracers of the underlying LSS. So gravitational wave events from black hole mergers of stellar mass, and the intensity mapping of the neutral hydrogen. And I will cover a few different applications we can do by studying these two tracers combined together. And I will shift from more astrophysics related topics to purely cosmological topics. So just to give a very, very broad introduction about multi-tracing studies. So sometimes people use the same word, two different words to mean the same thing. Sometimes people talk about multi-tracing, some other times it's multi-messengers, but technically these are two different concepts. So you can imagine, for example, you have a neutron star binary systems, they merge, you detect their gravitational wave signal coming from the merger. And then you might also have their electromagnetic counterpart. And in that case, you talk about multi-messenger because it's the case in which you're seeing the same event, so the neutron star merger, with two different eyes, with two different, in one case, gravitational waves and electromagnetic waves. So you have the same events seen with different eyes. When we talk about multi-tracer, instead, we are literally looking at two completely different things, two completely somehow unrelated objects. So for example, compact objects mergers and other maybe luminous tracers, other LSS tracers such as galaxies or the intensity mapping of some specific lines. So we're not seeing the same events, the same happenings with different eyes, but we're seeing different things with different eyes. And this is a very, very completely incomplete list of some examples from the literature where people have studied the cross correlation of different tracers such as gravitational waves, galaxies or other LSS tracers, intensity mapping, CMB or different types of galaxies and so on, to gather information about very, very broad range of fields. And it's very interesting because when you study the cross correlation of different tracers, you might explore paths that would never be able to be explored with just single tracer experiments. So you could either improve results that you might also gain with single tracer experiments, but with a worse capability, worse abilities, or you might even open completely new synergies, new paths that would not be able to be explored with just single tracer experiments. And the literature in this field, it's not so recent, but it's also not so old. So I would say that we are still at the very beginning, especially now that we have gravitational waves, which are completely new way to observe the cosmos. The synergies and paths to explore will be probably a huge number, almost infinite. So it's very exciting to see and to be aware of all the possibilities that one might explore with multi-tracing experiments, multi-tracing works. So just to give a very broad introduction to the tracers we explored in this work. So I will try during my talk. Okay, I will have to give some technical details, but in general, I'll try to focus on the concepts, but of course, if you have any question about more technical things or more details, just ask. But starting very, very broadly, describing these two tracers, gravitational waves, what we did was consider the resolved events, so we can pinpoint each merger. We're not talking about the gravitational wave background. We resolved the single mergers, and we studied gravitational wave signals coming from black hole mergers, as seen from the Einstein telescope. And how can we describe this tracer in a couple of sentences? The first sentence, it's probably very overused and it's used in every gravitational wave talk, but it's actually true. Gravitational waves are a new and unique way to observe the cosmos. They actually are. I mean, we started detecting gravitational waves less than 10 years ago, and we are definitely at the very beginning of this so-called gravitational wave astronomy, and the paths that could be open are again almost infinite. So it's very, very exciting because thanks to gravitational waves we can observe the cosmos in a completely new way from before. So it's an overused sentence, but it's true. We have one downside. If we have to look for a downside regarding gravitational waves, is that if we do not have an electromagnetic counterpart associated to the merger events of these two compact objects, they are characterized by a very bad localization, both on the angular side, so we're not very good at localizing them on the sky, but also, and this is what matters in this work we explored, we have also relatively strong uncertainty on the redshift localization. So for example, when we want to do tomographic studies, we have to take into account either for a big error on the redshift localization, or we're forced to take very large redshift bins because we are not very good at saying that event is coming from there. We have a quite huge uncertainty. So they're a completely new innovative window, but the redshift localization is quite is relatively bad compared to other observables. On the other side, we have the intensity mapping. So as many of you know, intensity mapping is a relatively new technique, and it allows to scan a relatively big paths on the sky in a relatively small amount of time. And you can do that because you decide to not resolving single galaxies. So you do not resolve the single objects. What you get is catch all the integrated emission coming from your objects from a specific observation line. So what we consider here is the well-known 21 centimeter line, which comes from the spin flip transition of the neutral hydrogen as observed by the SKA Observatory Mid-Band Survey. And thanks to the fact that we know very well the emission line, the wavelength at the emission, we receive something at a different wavelength. So it's very easy to reconstruct from which redshift the signal we are detecting is coming from. And this is very important because it allows us to perform a very refined tomography. So if we do some tomographic studies and we divide our redshift range in different bins, we can take very, very small slices, very, very thin slices for our intensity mapping tracers, because it's probably the most powerful point, the strongest point of intensity mapping. We're very, very good at reconstructing the redshift distribution of our observables. And this is very, very important because we have lots of information more when we can add more redshift bins, because we're able to reconstruct a much more detailed redshift evolution of our tracers. And we know that also with the H1 intensity mapping, we are very good at reconstructing the underlying LSS distribution, because the fluctuations of our line describe basically the fluctuations in the underlying distribution, and the specific wavelength of the line gives us a strong information on the redshift, as I just said. So these are the two tracers we considered. And we explored three different applications, again, as I said, from astrophysics to cosmology. So the first one is more related to astrophysics. So we know gravitational waves are characterized by this huge uncertainty on the redshift. And we try to understand whether we can better calibrate the statistical overall redshift distribution of our gravitational wave events by cross-correlating them with the intensity mapping, the H1 intensity mapping distribution. Then we go towards cosmology. We try to see if we can constrain some cosmological parameters, for example, W0, WR, if we think about dark energy. And then we go even towards more exotic aspects. So you might have heard about primordial black holes. They were very popular in the recent years. So what if the black holes that we detect merging have primordial origin? Would we be able to test this hypothesis by studying the cross correlation of these two tracers? So as you can see, it's three different topics, three different applications related to very, very different areas. So we try to explore them and see how well we would be able to answer these questions and how well compared to single tracing experiments. Before that, you have to be patient. Give me just 4 slides of more technical things. But again, I'll try to focus mainly on the concepts, but some equations are needed. So first of all, which is our observables? Because, okay, I just said we're studying the cross correlation of these two tracers, but how do we quantify how those two tracers are correlated? So what we consider our observables, we work in the harmonic space, and we consider the number counts angular power spectrum. So we have two tracers, X, Y, in our case, gravitational wave and intensity mapping. We perform a tomographic analysis, so we have different redshift bins, and the cross correlation of the first tracer X in these bins at I with the other tracers Y in the redshift bins at J is given by, with this notation, by these CLs, which depend on the primordial power spectrum and on these two window functions, one related to each tracer. And the window functions depend on the redshift distribution of the tracers. So how many objects, for example, for gravitational waves, how many objects we have along redshift. And in the case of intensity mapping, of course, we don't have number counts because by definition of intensity mapping, we do not resolve the single objects, but it's very easy to show that you can actually adapt this same formalism to the intensity mapping case. So for example, instead of a redshift distribution, you may take the mean brightness temperature distribution, which is still a function of the redshift and describes how much of that tracer you have along redshift. So the redshift distribution is a very important quantity needed to characterize your tracer. And then we have the number counts fluctuations, whose expression is actually quite complicated. It's just a slide full of equations. I'm not gonna show it to you now, but the only thing you need to know is that they depend on several effects. So you have the standard density term, which is directly proportional to the bias. Then you have velocity terms, so redshift space distortions or Doppler effects. Then you have lensing effects and other GR corrections such as time delays. So we take all of them into account. And one way to compute all of these CLs is by using, at least what we did, the multi-class code, which is extension of the well-known class code adapted to the possibility of cross-correlating different tracers. So how do we characterize a tracer? As I said, we take the redshift distribution. This is one important characteristic. And then we have the bias parameters, 3 different type of biases. So the first one, the one which has probably the strongest impact, is the standard bias parameter. So for a given tracer, the bias parameter described how mismatched the distribution of that tracer is respect to the matter distribution. So this is the standard bias parameter. Then we have to consider also for the lensing effects the magnification bias. So you may have a change in the observed surface densities of that of the sources of the tracer due to gravitational lensing. So you can have an enhancement of the number of objects you see, or a de-enhancement. So you have to take this into account to model lensing effects. And then we have the evolution bias, which actually appears in subleading terms, but usually describes the possible formation of new objects over time. So we have the redshift distribution, or the number density, or the mean brightness temperature for the H1 distribution, and then the tree bias parameters. So once you have these four quantities, number densities and the tree bias, in this formalism you can perfectly characterize a tracer. So when I talk about tracers, in practice, I'm talking about any observable that you can characterize, for which you can characterize these four quantities. Here you can see their distributions for the tracers of these works. But then the CLs I showed you before are the theoretical ones computed with the multiclass. In reality, you have, of course, noise sources, and they might also be very, very strong. So you, of course, you need to take them into account. On the gravitational wave side, one of the main noise sources is the standard shot noise term, so 1/n. And then this is, it has quite a strong effect on your observed objects, on your theoretical observed CLs. And then, as I said before, you have also the fact that you're not very good at localizing your objects. So you need also to take into account the fact that you're not good at localizing them. And also you might commit errors on the assumed cosmology, because what you measure is the luminosity distance, and then you switch from that to the redshift, assuming a cosmology. But if you mess up with the cosmology estimates, you mess up with the redshift. And so you may associate those events to the wrong redshift bins. So one way to take this into account is to take very large redshift bins, because in the formalism I showed you before, the only important thing is that each event is associated to the right redshift bin. So by taking very wide redshift bins, you're more safer, in the sense you're more guaranteed that even though you have a big error on that localization, your event will still fall into the right redshift bin. Of course, this is not a way to ignore that error, that problems, because the wider the redshift bins you take, so the fewer redshift bins you take, the smaller amount of information you put in, you give to your pipeline, and so your forecasts will be worse. Indeed, by taking larger redshift bins, our results that I will show you later are degraded even by 40 or 50% compared to the case in which you can take smaller redshift bins, but you have to take into account this localization errors if you do not have an electromagnetic counterpart. So this is the downside of gravitational waves, reflecting also on the ability to forecast whatever you want to forecast. On the other side, intensity mapping is characterized, you have to take into account beam effects. So basically a signal suppressions at small scale smaller than the full width at maximum. So it's sort of exponential, and you have your signal degrading at smaller scales. Then you have to take into account, of course, instrumental noise of your instrument. And then people who work with intensity mapping know that one of the difficult, most tedious points regards the foreground. So we have this very strong foreground emission. We have to clean it because the signal we actually want to detect is well below the foreground noise. So this must be taken into account. But of course, the scope of our work does not concern the modeling of the foregrounds, but still we need to take them into account. So our approach, and if you have questions or on the details, please ask. But just to put it very, very simply, basically we assume that foregrounds are going to be cleaned, and we assume that there will be some errors in the foreground removal procedure. So we clean the foregrounds, but not perfectly, of course, and we plug in that error that we expect would be committed by this cleaning procedure. So we don't model the foregrounds, but we model the error with which the foregrounds would be cleaned, in a nutshell. So the one last slide of intro and technical stuff, and then we will move to the interesting parts. What we use is a Fisher approach. So in all our tree analysis, we perform Fisher analysis on different parameters. Which ones, it will depend on the applications, but in general, in all of the three cases, we gather together all our possible observables, which you can see there are many because they are the observed CLs for all tracers, so intensity mapping and gravitational waves, also in auto tracers. So we have all the combinations of our tracers and all the combinations of redshift bins, so you can organize them all together in a matrix like this, whose dimension is given by the sum of the redshift bins of those two tracers. And we build the well-known Fisher matrix, and the Fisher matrix gives you a marginal error on the estimation of that specific parameter alpha. So it tells you more or less what you would expect the error on that specific parameter would be, considering those specific instruments you're considering, in our case, Einstein telescope and the SKA midband. So with those experiments and with these two tracers, how well would be constrain, how well would we be able to set constraints on those specific parameters? Again, which ones depends on the application we explored. Our redshift range is this one, 0.5, 3.5, which more or less should be the redshift range of the mapping performed by SKA. And we take, as I said before, redshift, the ability to localize the redshift of our to describe the redshift distribution of our observables is very different. So for gravitational waves, we take very large bins. So we have only 3 redshift bins in this range. For intensity mapping, instead, we take 30 redshift bins instead inside the same redshift range. So you can see here it's a striking difference. And so we take this all these bins, perform all the possible correlations, and these are our observables. So the theoretical CLs plus all the noise sources I mentioned before. And okay, this is the necessary but technical part. Now we move to the nicer part. So application number 1, more astrophysics, and regards, as I said, the calibration of the statistical redshift distribution. So just to clarify one point, we're not aiming at better constraining the redshift localization of each gravitational wave event, but we try to better calibrate the overall redshift distribution. And the general idea, which was already explored to calibrate photometric samples of galaxies in some works like these ones, but to our knowledge was never applied to gravitational waves, is this one. The main idea is this one. We have 2 different tracers. One of the 2 tracers has very strong and powerful redshift information, so it can be our spectroscopic sample. And then we have a second tracer whose redshift distribution is almost unknown or poorly known. And here in this picture by this work of Alonso et al., you can, I think this perfectly gives an idea of the main concept we rely on. So we have many very thin redshift bins for our well-known tracer. And then we have the distribution of our unknown tracer. And we cross-correlate this one with all the many thin redshift bins of the well-known tracer. And then if we look at the CLs, both as a function of the multiple and of the redshift, we can see that the way they are correlated from one another, so the way our CLs behave, perfectly resemble the redshift distribution of our unknown tracer. So this is the main idea. A tracer whose distribution is very well known, could it help in better reconstructing the redshift distribution of the unknown tracers? And you can see that by looking at their cross correlation, actually you can gain, you can gauge the distribution of the unknown one. So it can actually help, at least in theory. Now let's see in practice what we did. We take a fiducial. We have to start from a fiducial redshift distribution of our gravitational wave events. we model it as a piecewise function. So it's this one in blue. It's made of very, very small steps. Each step is characterized by an amplitude. So this is the parameter we try to constrain. So we have 30 steps, as many as our intensity mapping bins. And we perform a Fisher analysis on 35 parameters, the 30 amplitudes, one for each step of the piecewise gravitational wave redshift distribution. And then we take into account cosmology parameter, AES and S, the biases of our two tracers. And then this is basically the amplitude on the errors due to the foreground removal procedure. We perform the Fisher analysis and we try to estimate the errors with which these amplitudes would be able to be constrained. What we get is something like this. So you can focus on the central plots. So on the left side, we have the fiducial redshift distributions with the error bars on the amplitudes for an F-sky of 0.5, which is the fiducial value for SKA, and 15 years of observation time for our gravitational wave experiment. And you can see already here by eye that constraints at lower redshift, of course, are much, much better than a higher redshift, and then at some point you're not able to constrain anything. And here on the right side, you can see the relative errors on the amplitudes as a function of the redshift for different observation times. So for example, you can see that for 10 years of observation, your relative error would be around at lower redshift 0.5 or 0.4, 0.3 even for a higher amount, a longer observation time. So you would be able to set constraints on at lower redshifts on the amplitude of your gravitational wave redshift distribution of around 20% of the fiducial value. Why would we care about this? Well, different redshift distributions might derive from different astrophysical models, or even beyond that, of course. For example, if you think about primordial black holes, the redshift distribution would be quite different than the astrophysical one. But even if you just stick to standard astrophysical scenarios, different scenarios might be related to different models. So you might be able, in principle, the better you constrain the amplitudes and this redshift distribution, the better you are at discerning different scenarios. So this is quite important. At least at lower redshifts, you're able to set some relatively decent constraints on the distribution of your gravitational wave events, and hopefully constrain different astrophysical models or even models beyond astrophysics. And this is the first, let's say, the first point of this work, the first application. So constraints on astrophysics, quite interesting, but only at lower redshifts. Now I move to the second application. I will be much quicker on this and then focus the rest of my talk on the third one. So if we move towards cosmology, what if we have a possible time evolution for dark energy, so the W0, WA parameters, how well the cross correlation of these two different tracers, GW and the intensity mapping, would constrain the W0, WA parameters. So what we do here, again, we perform a Fisher analysis. We don't model our redshift distribution as a piecewise function this time. We take the fiducial one. And we, in our Fisher loop, we plug in, of course, the W0, WA parameters, then several other cosmological parameters, and again the bias parameters and the foreground noise amplitude. And the contour plots we get are this one. So here on the left side, you can see for an F-sky of 0.5 with or without Planck prior on the other cosmological parameters. These are the constraints we get. Of course, with Planck prior, constraints are tighter. And on the left side, we assume we plug in a Planck prior, and you can see, of course, for different fractions of the sky, how the contours change. And of course, the more sky you observe, and the better your constraints are. So how do these results compare with single tracer only experiments, we see that these constraints more or less are in agreement with the intensity mapping only experiments. Still, by performing this cross-correlation analysis, we might get rid of, overcome some systematics that might affect intensity mapping only experiments. And on the other side, this type of studies still offer an alternative way to test those parameters and to test those scenarios. So they give an alternative today in this investigation in this field, but maybe hopefully freer from systematics and other problems. So regarding at least the dark energy and W0WA parameters, we set interesting constraints, but in this case, we are not able to perform better than intensity mapping only experiments, but it's still an alternative way to test those parameters. Last application, this is personally my favorite one. So I will start with a very, very broad introduction on primordial black holes. So as I said, we started from astrophysics, moved towards cosmology. Now we're still exploring cosmology, but with more exotic topics. So primordial black holes were firstly theorized between the 60s and the 70s by Zeldovich, Novikov, Hawking, and Carr. And the way you can form a primordial black holes, theoretical people have theorized many, many models, but in general, the main idea is the following. We know the early universe was very, very dense. What if we get even overdense regions in the early universe, and those regions, since the early universe is already very dense, those overdense regions might have the right characteristic to undergo gravitational collapse and form a black hole. So we might have these black holes forming in the very early universe, surviving up to today. And maybe if they are in binary systems, they at some point they will merge, and we might detect that merger through their gravitational wave emission. So when they were firstly theorized, primordial black holes got very popular because people starting asking, what if the dark matter we are looking for is composed of primordial black holes? And it was a very, very popular idea at the time. Then, time by time, some constraints of massive observational constraints of on massive compact objects were starting to pop up. On the same times, the WIMP paradigm raised, so the idea that dark matter might be composed by these WIMPs also got popular. So the hypothesis of the primordial black holes composing a significant fraction of the dark matter lost interest and got lost over decades. And then what happened in 2015, we know we detected the first gravitational wave signal from a black hole merger in the stellar mass range, around 30 solar masses per black hole. And also at the time, among all the observational constraints on the possibility that primordial black holes might form a significant fraction of the dark matter, the range around 30 solar masses or a few tens of solar masses was not very well constrained, or anyways, constraints in that mass range were a bit disputed. So again, after this event, the interest of the scientific community revived toward primordial black holes and the idea that they might compose a significant fraction of the dark matter. Nowadays, we are quite sure that at least in the stellar mass range, they cannot compose a significant fraction of the dark matter. But you know, as anything, there is not only black or white. So what if some primordial black holes exist? They don't compose at all a significant fraction of the dark matter, but maybe there are some, or maybe not. And confirming or excluding the possible existence of primordial black holes might set constraints on, for example, early universe models that might predict or not predict the formation of primordial black holes. So even though we're confidently sure that they are not composing a good significant fraction of the dark matter, it's still of interest to study their possible existence or not, or to exclude it, to set constraints on other cosmological models, for example. And the idea of this last application is, what if we study the cross correlation of gravitational waves and other LSS tracers, such as galaxies or the intensity mapping? Would we be able to determine the origin of the progenitors of the black holes that we detect merging through their gravitational wave signals? So how studying their cross correlation of those gravitational wave events and other LSS tracers, how could it give us information on the origin of those black holes? So this was already explored in the past, but in this work, we consider the intensity mapping as our LSS luminous tracer. So why should this cross correlation tell us information about their origin? So I'm gonna give you some very general idea on this. So I'll focus on the concept behind it. So the idea is that depending on the origin of your binary black hole, so whether it's astrophysical origin, so we have black holes coming from the endpoint of stellar evolution, or whether they have a primordial origin, so they were formed in the early universe, our gravitational wave resolved events might trace the underlying LSS in very different ways, depending on the scenario. So here you have a picture, this figure from the Millennium simulation of the LSS. And so what if our black holes have only astrophysical origin? Where would you expect them to come from? So in this figure, definitely not on scale, we can see that if our black holes had an astrophysical origin, of course, we would expect the bulk of our gravitational wave events of a black hole merger of stellar origin to come from those halos in which we have a higher amount of stars, because the more stars we have, the more black holes, the more stellar black holes we will have, and then the higher number of mergers and gravitational wave signals. So we would expect under an astrophysical scenario to mainly have events coming from those very massive luminous halos, highly star-forming halos. And one key parameter to look at is the bias parameter. As you know, the bias parameter for a tracer tells you what's the mismatch in the distribution between that tracer and the underlying matter distribution. So our gravitational wave events, since we can pinpoint them, we can characterize them with a bias parameter, which tells us how they are distributed. And their bias parameter more or less will be the bias of the host halos. And if those gravitational wave events under the astrophysical scenario mainly come from an astrophysical scenario, they will come from this. They will mainly come from these very massive luminous halos. The bias parameter of those halos is known to be well above unity. So the bias of our gravitational wave events will be above unity. And this is very important. So we have this scenario, astrophysical scenario, with this prediction on the bias parameter. Now, what if our black holes have primordial origin? We have two scenarios, the so-called late and the so-called early primordial scenario, depending on when the binary is formed. So if we think about a so-called late primordial scenario, under this scenario, we have that the black holes themselves are primordial, but the binary system is formed in the later universe. In this case, if the binary is formed in the later universe, we know that this might happen when two black holes pass one close to the other. And if the relative velocities are low enough, they can get gravitationally bound, form a binary system that at some point will merge. And then we will detect the gravitational wave emission. So lower velocities, so velocities low enough to allow for this binary formation. They are low enough in lower mass halos, which are darker halos, tracing mainly the filaments of the underlying LSS. So we would expect these signals and these binaries to form and merge mainly from this type of halos. And we know that this type of halos are characterized by lower value of the bias parameter, well below unity. So the gravitational wave events can be associated to a value of the bias lower than unity. So up to now, we have two different scenarios with two different values of the bias parameters. And just to clarify one other thing, I'm not saying that, let's imagine we only have primordial black holes, and even like the dark matter is composed only of primordial black holes. I'm not saying that here, for example, we would not have primordial black holes. They would be also here. But here, those velocities would be too high to allow for binary formation, because what we see is not just the random primordial black holes moving around, but we need a binary system and then a merger. So here we would have lots of primordial black holes, but we wouldn't be able to detect many events because it would be very difficult for a binary system to form. So here we would not see anything, even though we would have primordial black holes themselves, but we need lower velocities for the binary formation to happen. So these are two different scenarios. Then third scenarios, what if both the black holes and the binary systems are formed in the early universe? So this is the so-called early primordial scenario. In this case, primordial black holes would be very good tracers of the dark matter, so they would be distributed almost everywhere, tracing it very well. And by definition of the bias, the bias parameter associated to those resolved gravitational wave events coming from their merger would have a value of around unity by definition of the bias. And this happens because the binary is already formed in the early universe, so they don't care about the relative velocities or dispersion velocities inside the halos. So we have three completely different scenarios, one astrophysical and two primordial, and each of them is characterized by a different value of the bias parameter for the gravitational wave events. So now at this point, you understand that the key parameter to look at is the bias parameter of those redshift, of those gravitational wave events. And the question we ask is, how well would we be able to set constraints on the value of that parameters? And would the error on that parameter be small enough to distinguish between different values corresponding to different scenarios? So the answer is yes. What we did here is again perform a Fisher analysis over all the cosmology or all these cosmology parameter. The biases, of course, the key parameter now is the bias of our gravitational waves, and then again the amplitude of the foregrounds is plugged in. And here, okay, I will guide you through these figures. So results are expressed as a function of this gamma parameter. So we have two different scenarios, one astrophysical and one primordial. So one is the fiducial scenario, the astrophysical, for example. And we ask ourselves, would we be able to distinguish this fiducial scenario from an alternative primordial one? So for each scenario, we define this gamma PBH parameter, which is basically the fraction of detected mergers of primordial origin among all the mergers we detect. What does it mean? Basically, this gamma is 0 if among all the mergers we detect, all of them are given by black holes of astrophysical origin. And if this gamma is 1, we assume that all are, we are in the extreme case in which we assume that all the black holes we detect merging have primordial origin. So of course, results will depend on how many primordial black holes we have. And we can see that for different fractions of the sky observed and different value of this gamma parameter, the signal to noise ratio that we get are quite optimistic. For example, if we set for an SF sky of 0.5, our fiducial value, which more or less corresponds to this line, we can see that the signal to noise ratio of around unity corresponds to a value of the gamma parameter of 0.2. This means that we would be able to detect the imprints of a population of primordial black holes that forms only 20% of all the mergers we detect. So if we have 20% or more of primordial black holes, we would detect those imprints with the signal to noise ratio of unity or higher than unity for higher fractions of primordial black holes, this for 10 years of observation. And a similar picture can be given by the right side plot. So for different observation years and different value again of this gamma parameter for fixed F sky, you can see that the signal to noise ratio of around unity can be reached for around 10 observation years, for a few observation years, for a value of gamma around 20%. And for even a smaller amount of observation years, even just with 2 years of observation, you would detect the imprints of a population of 50% of primordial black holes among all the mergers you detect with your instrument. And personally, I think this is my favorite result, the most striking, because of course, If you go even to lower percentages, you will not be able to detect the imprints of those primordial black holes. So if you have 5%, 10% of primordial black holes, at least in a relatively decent amount of time, you will not be able to set constraints on those abundances. But again, at least with 20% of primordial black holes, you would, according to our results, you would be able to say, yes, we have 20% of primordial black holes among all the signals we receive, or no, we don't see the imprints of that population. So I think that's very, very interesting. And again, this is distinguishing an astrophysical scenario from an early primordial scenario. Similar results are reached if you want to distinguish an astrophysical scenario from a late primordial scenario, or again from a mixed scenario composed by a mixture of early primordial black holes and late primordial black holes, because again reality might be in the middle. So you have primordial black holes whose binaries are formed both later and in the early universe, and you can also have astrophysical scenarios and so on. But usually you would be able to distinguish imprints of a relatively small population of black holes, and I think this is quite interesting. And I will shift to the conclusion just to recap everything once again. On the astrophysical side, we would be able, thanks to gravitational wave cross intensity mapping, to better calibrate the statistical redshift distribution of our gravitational wave events, resolved events coming from black hole mergers, especially at lower redshifts. And this is one application for which you need to go in cross correlation. You cannot do this just with the gravitational wave events itself by construction of that method. Regarding constraints on the dark energy parameters, they're not competitive. They could be done also with intensity mapping only experiments, but still you might try to get rid of systematics, and thanks to the cross correlations, and they might provide still an alternative way to test those parameters. And finally, again, another application that would be possible by construction only through going in cross correlation with other LSS tracers, you would be able to detect the imprints of a small population of primordial black holes among all the detective events in a relatively small, let's say, human amount of time. So from astrophysics to cosmology, this is what we explored. And I thank you for your attention. And if you have any question, I'll be glad to answer. So thank you for your attention.
Well, thanks a lot for the talk. It was great stuff.
Thank you.
If you have a question, you can raise your hand reaction, or you can just open your microphone. Well, no one so far. So people are still gathering the votes, I guess. So I'll start with a basic question about gravitational waves.
Yeah.
So you said there is a cosmology dependence on the redshift detection, the measurement of gravitational waves. So for the electromagnetic traces, we would know the redshifts, but then the distances would be the cosmology dependent thing. So how do you measure the redshifts of gravitational waves if you don't have the electromagnetic counterpart?
Well, what you detect, what you can directly measure with gravitational waves is the luminosity distance. And then you shift to redshift with a luminosity distance redshift relation, but that relation relies on the values of the cosmological parameters. And of course, once you assume, you need to assume a cosmology to shift from luminosity distance to redshift. And so the point I was raising is that if you are not plugging in the right cosmology, you will associate a slightly biased redshift to your events, and that might cause you to associate those events to the wrong redshift pins. So the way you can take that into account is either building, trying to estimate an error on the assumption, on the possible wrong assumption on the cosmology, or you just take very large redshift bins. So if you assume that you're not committing a huge error on your cosmology by enlarging your redshift bins, you're still safe, because even though if you associate the events to the wrong redshift, still they might fall into the right redshift bin. And as I said before, like what we care about is that each event is associated to the redshift bin. That's what matters, because we associate those events in that bin with those events from the other array tracer in the other bin. So as long as they fit into the right redshift bin, we are safe. But of course, the larger the redshift bins and the lower amount of information you give, and the more pessimistic your results would be. But yeah, to come back to the question, the problem with the cosmology is that you directly measure a luminosity distance for gravitational waves. And if you want to know the redshift, you need to pass through cosmology and assume some values for the cosmological parameters. And if you mess up there, you mess up also with the redshift.
Okay, I see. Thanks. Anyone else has a question? We don't see anyone having raised their hands, so I'll ask another one. So you said that so all of dark matter can't be composed by primordial black holes. What kind of order of magnitude of dark matter can be still composed?
So focusing on the stellar mass range, yeah, now constraints exclude a significant fraction of the dark matter being composed of at least stellar mass primordial black holes, because you have both CMB constraints and other observational constraints. What would be possible? So these constraints, actually, if you see over time, every now and then new constraints pop up, then maybe a few months later they might be disputed and so on. In the stellar mass range, I'm not sure about the true number, but I would say a very, very small, a relatively small percentage of primordial black hole might compose the dark matter. Or in other words, they have not been excluded yet up to, I would say, I might be wrong, but just a few percent or even less. So okay. We're talking about very, very small percentages, if I'm not wrong.
Okay.
I might be wrong, but I don't think so. In the stellar mass range, we're very safe that for sure they're not significant. But again, you might even have one primordial black hole, and you rule out all the models that predict the impossibility of having primordial black holes. So
yeah,
they might not be interesting for the dark matter, at least in that mass range, but they can be interesting for other things.
Yeah. David, you want to ask something?
Thanks for the very nice talk. I guess I wanted to go back to your point one.
Yeah.
And now I have to make sure that my memory isn't escaping me. I mean, there are a large number of optical spectroscopic redshifts that are going to cover a large angular range and a large redshift range. Like DESI is already, I mean, EBOS already exists. DESI is going to go deeper soon with this as well, to cover the redshift range that you have there in your figure, for example. So why intensity mapping where it's harder? getting a signal out of an intensity mapping survey is intrinsically harder because you have foregrounds, right? And yeah, to be sure that the signal you have is really 21 centimeter emission and not you know, foreground emission is tough. Whereas spectroscopic redshifts, optical spectroscopic redshifts is tried and tested technology, which is pretty reliable for. So
yeah, no, I agree. So let's say that the very strong point with intensity mapping is, again, the ability to perform a very, very refined tomography. With the spectroscopic galaxy samples, I'm not sure about how thin your bins can be, probably more or less like that, or even small, but then you have to take into account some noise related to the small bin. But the main idea was to, you know, intensity mapping is very foregrounds. I mean, probably especially foregrounds are the most difficult task to tackle, but at some point, hopefully, we will be able to manage those very well. And once we're able to manage those, the intensity mapping of the neutral hydrogen is going to be a very, very powerful and enormously strong tool with which we can do sorts of things, and we have lots of experiments set for the intensity mapping of the neutral hydrogen. So our idea was their main point is the ability to perform a refined tomography. We have several experiments set for already running for this observable. The foreground situation is very, very complicated, of course, but like everything in physics, hopefully with the time and efforts, we might be able to control them. So it felt natural and curious to ask ourselves, okay, we have this thing in which lots of the community is working on. So can it help us or not? So the main idea, yes, the main reason was the very sliced tomography. Why exactly intensity mapping and not other spectroscopic galaxy samples? I would say, why not? In the sense that it's there. At some point, we will manage it, and it felt natural to wonder. Since it's a very, very powerful tool and very popular tool that it's being explored, it felt natural to wonder what can intensity mapping of the neutral hydrogen give us in regards of these terms. So of course you can do the same idea and the same thought process with other spectroscopic samples. I guess the tomography you would get would be the way you can perform a slice tomography would be more or less similar. So it would be for sure interested to do also that, but yeah, I agree that the main difficult point, the highest mountain to climb in this case, it's the foreground's emission. But lots of people are working on that, and hopefully we will be able to manage those. And once we do, we might do even interesting things. And then intensity mapping can provide an alternative way to test this in a parallel way to other spectroscopic samples.
Okay, thank you.
Thank you.
Julio?
Right, I have a follow-up question. You might have explained this and I've missed it, but yeah. So because of the foreground removal will be very tricky for intensity mapping, how much of that do you think would affect the results you forecasted here? Like having not completely removed foregrounds, how much should they affect the forecast?
Yeah, here you need you do need to model the foregrounds very, very well, because the signal you're measuring is well below the very bright and strong foreground emission. So if you're not able to model well the foregrounds, it's gonna be very, very difficult to have a reliable signal. The way we model the foregrounds is, I can show you very quickly. It's something like this. It's let's say, as I said, we don't model the foregrounds. We model the error with which we would be able to clean our signal from the foregrounds. So the way we build the error is something like this. We have this amplitude, which is the parameter I plugged in before, and then a function which depends on the scale you're looking at. And we took from this work by Alonso et al. This sort of scale dependence, which more or less gives you, this is our assumption, this more or less gives you an error of 12% at larger scales, because you have a stronger foreground problems at larger scales, and then more or less 4% at L equal 100, more or less. And this also the way we set this amplitude, of course, we plugged in our Fisher pipeline, because we set it to a fiducial value, but it might not be the correct one. And more or less, it has to relate to the amplitude of your CLs. So 12% at this L or 4% at higher Ls. But again, this I don't want to get too technical here, but these amplitudes, it's more or less an average of your CLs. It cannot be exactly those CLs. So in other words, if this is 12% of your CLs, if you just plug in for each CL and for each L that your error is exactly 12% of your theoretical CL, you're actually boosting the signal, because your observed CL is theoretical one plus the error, But if the error is exactly 12%, for example, of the signal, basically your observed CL is 112% of the theoretical one. So you would, by the stronger the error, the more boosted would be the signal. So more or less this amplitude must relate to the order of magnitude of those CLs, but it cannot be exactly then, otherwise you end up boosting the signal, introducing a noise source. But it's the foreground problem. It's the strongest one. It's the more important to overcome, because again, we made these assumptions based on previous efforts of the community. And still lower scales are affected a bit, but this assumes that you would be able to do things this good. If you're not able to manage appropriate foreground removal procedures, you might mess up quite a bit, because again, the signal you want to observe is well below the foregrounds you want to get rid of. So I would say that the most important thing to achieve all of these things, the most difficult and yeah, the most important one is to be able to deal with the foreground removal in an appropriate way. And here we try to take into account all of that. But yeah, it's probably the main point.
All right, thank you.
Thank you.
Okay, thank you. So already past the hour. If there's not any other quick question or comment, I'd like to thank Giulio again for the nice talk.
Thank you.
And
thank you for having me here. It was very nice.
yeah, it was a pleasure.